So the topic is compact sets. This is actually an extremely important concept in analysis. Okay. So first, a quick intro to open sets. Has anyone heard this term before? Open set? Open set? No? Okay. So I'm only going to just touch on this. Okay, so here's the definition. Let E be some set. We call E open if given any point in E, there exists a delta such that the neighborhood, this delta neighborhood of X is contained in E. Okay, so here's an example. If we look at the open, the open interval 0, 1. Okay, somebody gives you a point inside 0, 1, and you say, oh, I can find a delta neighborhood of X that is contained in 0, 1. Right? If somebody says, I give you the number 1/4. And you say, okay, I'm going to take my delta to be 1/8, and the eighth 1/8 radius neighborhood of 1/4, certainly lies within 0, 1. Okay, and you see that you can do that for any point, right? Somebody gives you this thing, you can find a delta neighborhood that's contained inside of it. Okay, so this is an open set, right? Any open interval is an open set. Okay. And this condition is also called every X is an interior point. Every X is an interior point. So being an interior point means that there's some neighborhood of U that's interior to the set, right? X is an interior point if there exists some neighborhood of X that's contained inside of U. Somebody give me an example of a non-open set. What set? Can you give me an example of a set where there's some point or points that are not interior? You think, oh yeah, well.
A closed interval?
Closed interval, right? So let's look at the closed interval, 0, 1. Well, what points fail to be interior? 0 and 1, right? The endpoints, right? I can't find any delta neighborhood that's contained inside the set, right? No matter what delta neighborhood I take, no matter what delta neighborhood I take, it extends outside of my set. So these guys are not, right? 0 and 1 are not interior. So this set is not open. Right? I can't, no matter what neighborhood I take, I can't find any neighborhood of 0 that's contained entirely inside the closed set 0, 1. Certainly I can do it for some of the points, right? If you give me this point, yeah, it's interior. And if you give me this point, yeah, I can find this neighborhood. This point is interior. This point, so there are a lot of interior points here, but to be open, all points have to be interior. Even simpler example. Here's my set. A set of 1 point. Right? That's not an open set, right? Because no matter if my set consists of this 1 point, then no matter what neighborhood I take, it's going to contain guys that are outside my set. Right? I can't find a neighborhood of this point that's interior to my set because my set contains a single point. Okay. My set contains no neighborhoods. Okay. Is this making sense? Okay. Okay. And maybe the simplest open set would be the whole line, right? The whole line is certainly open because if you take any point in it, you can certainly find a neighborhood of that point contained in the whole line. Okay, another definition. We call F a closed set. Closed set if the complement is open. So this is the notation for a complement. Complement meaning everything outside of that set. So FC means everything in R that is not in C. I should make a comment that we consider the empty set to be open. Right? We consider the empty set to be open because it sort of satisfies the condition trivially. Right? Given any point in there, can you find a neighborhood around it? Well, there's no points in the set that you need to check for this condition. So sort of automatically it's considered to satisfy the condition. Okay, so the empty set is considered an open set. Just by logic. Logically. Okay. Okay. So okay. So for example, in fact, R is a closed set because R is the complement of the empty set. Okay.
I thought you said the whole line was an open set.
I did. So in fact, R is an open set. R is an open set also. So that's the joke, that how are sets different from doors? A door can be either open or closed, but not both simultaneously. And sets can be both open and closed simultaneously. So a set could be open, it could also be closed. These aren't exclusive. Yeah, these aren't exclusive ideas. Okay. So there's even a term for it, clopen. Okay. There's even I've never seen this term used outside of the movie where Hitler tries to learn topology. I think I mentioned it before. Did I mention it? Like there's this like they've taken this old World War II movie in German, and Hitler is angry about something, and so they've redubbed it so that he's talking to all of his aides are actually like topologists, and he's trying to learn topology from them, and he says like, so blah 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 blah, and so this is an accumulation. No, this is an open set, and because it's open, it's not closed. And then one of them says, "My Führer, it is also closed." And he says, it's like glaring. Anybody who thinks this is This is not bullshit. Get out. Get out right now. And then, like, there are some people who are left. He starts berating them. Like, you guys are supposed to be the best topologists in the world, and yet you come up with this stupid terminology. Well, anyway, I recommend it. Okay, so yeah, unfortunately, closed and open are not mutually exclusive. Okay. Okay, so that's all I want to say about open and closed, okay? Maybe it will be explained in more detail in one of the final projects, I don't know. Okay, so now we're gonna do something which is, this isn't exactly heading towards compact sets, but it will be used, continuity and open sets. So the notion of open set actually gives us a different way, a slightly different way, well, actually a quite different way of thinking about continuity. Okay, so remember, we have two definitions of continuity already, right? One is the delta epsilon definition, right? The neighborhood maps into, given an epsilon neighborhood here, you can find a delta neighborhood that maps into it, definition. And then the other is the sequential continuity, right? So this, now we're going to introduce yet another variation on continuity, which maybe could be called topological continuity. Okay. And it's like this. So you have some function, reveals. F is continuous if and only if, well, actually before we get there, I need to define something else. Okay, let me put it here. Okay, so let me first make a definition. You have some function from R to R, and you have some subset of R. So function from R to R, and you have some subset here. Suppose it's this set here. Okay, you have some function like this. We call the set of x in R such that f of x lies in E. The preimage of E through F. Okay, or sometimes people just call it the preimage of F. So that's sort of imprecise. The preimage of E through F. Okay, and it's denoted by F minus 1 E. So you're pulling E backwards. You're pulling E backwards through F, and you're saying what guys get mapped into E. What points get mapped into E. So it's everybody whose outputs lies in E, whose outputs lie in E. Right. All points whose outputs lie in E. And so he says, anybody who thinks this is bullshit, get out. Right? Those who stay think it's not bullshit.
Preimage of E through F.
Yeah. Preimage of F.
The same thing.
Yeah, so I think people tend to use, this is, I think, colloquially more used. You say the preimage of F. Right? The preimage of F. But I think more properly you say this is how you describe it, because you you have to say what set is being pulled back through the function.
So are we going to use both of them in this class?
Mhm. Okay. Okay. So again, right, you just look at what points get sent to E, and that's the pre-image. That's the pre-image. Okay. So now we can explain. We can put down the theorem. Here's a function from R to R. F is continuous if and only if given any open V in R, F inverse of E is also open. Okay. In other words, whenever you have an open set over there, when you pull it back through the function, the pre-image is still open. If that happens, then your function is continuous. This is in fact a perfect description of continuity. Yeah.
Is continuous on the block interval?
Continuous on the whole set. So on. Okay, so let's think about it. Let's think about it. So let's remember, right? So going forward, we have the property. So we know F is continuous on R. So, like, given any, what does that mean? That means that if we take any point x and look at its output, and we take any epsilon neighborhood, there's a delta neighborhood that gets mapped inside there, right? There's a delta neighborhood that gets mapped inside there. Right? That's our current understanding of continuity, right? If you're continuous on R, then at every point you're continuous at every point. Continuous at every point means that if you look at the output and you take some epsilon neighborhood around it, then there's a delta neighborhood around here, right? So given any epsilon neighborhood of f of x, there exists a delta neighborhood of x such that f of the delta neighborhood lies inside of the epsilon neighborhood of the output. Right? That's continuity. Okay. So we're hoping that that is going to tell us that the pre-image is open. We're hoping that that's going to tell us that the pre-image is open. Okay. So let's think about that. Right? You have some open set V here, and you have the pre-image, F inverse V. Okay. You have the pre-image F inverse V, and you take some point in there, and you're hoping to see that that's an interior point, right? You're hoping to see that that's an interior point. So here's what we want to do. Given, so let V be open, let X be in the pre-image, we want to show that X is interior to F inverse V. So I'll let you think about it. And see if you can figure out why that's gotta happen. Pick some guy in there. In fact, that guy is interior to the set. Think about it for a couple minutes and see if you can figure it out. I'll walk outside. We can talk to each other.
When are you registering? When are you registering for classes?
I'm not curious.
Oh, you're going to Silicon Valley. Awesome. Which company?
I don't know.
Mm-hmm. I'm very jealous of you actually.
Excited for I wanted to take care of Christmas.
Yeah. No, I want to be done with that in 4 years. And I want to extend it.
You switched to your son's right?
Yeah. I was supposed to check it and go, but
See.
yeah.
I don't know. I was like, Professor O was my advisor, and I went to his class and he's like, so I don't think I can graduate on time. We gotta like, move a bunch of things around. He's like, no, you can do it. And I was like, okay. Then I called my mom and was like, I don't think I can graduate on time. I'm so sorry.
Okay, you guys figured it out? No? No?
Oh, I didn't.
You didn't. Anybody figure it out? No? I wonder, I sort of wonder, I was talking with a student outside, I said, I have no idea what they do inside there after I leave the classroom. Maybe they all like get up. They all like, I don't know what you guys are doing. Yeah, Ron.
So doesn't that follow just from the definition of continuity?
Yes, absolutely. It's almost trivial, right? Yeah. So you want to show that this guy's interior, right? So you know that this is open, right? This set is open. So what? Since the set is open, every point is interior. Well then, there is an interval here, right? Right. So since V is open, there exists an epsilon neighborhood of f of x contained in V. What do we do with that epsilon neighborhood of f of x, Relly?
You just map it to x.
We know that,
Yeah.
we know that there's, by continuity, there's a delta neighborhood here, right? By continuity, there exists a delta neighborhood of x such that f maps that guy inside the epsilon neighborhood. right? Which is inside of V. Right? So what does that tell you? Oh, hold on. What does that tell you? That tells you that there's a delta neighborhood here that gets mapped inside of V. Right? So what does that tell you about the delta neighborhood? That the delta neighborhood lies inside the pre-image of V. Right? Because the pre-image of V is everybody who gets mapped to V. This neighborhood gets mapped into V. So it's in the pre-image, right? So yeah, X lies in a delta neighborhood that lies in the pre-image, and so X is interior. To the pre-image. Okay, so the pre-image is open. Right? We've shown that if you choose anybody in there, then it's interior. Any point of the pre-image is interior, so the pre-image is an open set. Any questions? Any questions? The notation, I think, is a little dense today, so feel free to say that the notation is overly dense. Right? The picture is what you want to think about. Right? Here's X. Here's V. Right? X lies in the pre-image of V. Right? Here's f of x. F of x lies in V. Right? So you say, okay, well, look, we're trying to show that this guy is interior. Trying to show that this guy is interior. Well, we know that that this lies in the open set, and so there's an interval around it. Right? This guy lies in this open set, so it's interior. Right? This is interior. And then by continuity, right? So there's some delta neighborhood around it, right? That's contained in V. And then by continuity, you know that there's a delta neighborhood here that gets mapped inside that epsilon neighborhood. Right? But that means that this whole thing lies inside of the pre-image. In that case, X was interior. Okay? So that's the succession of pictures you want to think of. Okay. Maybe I can get through the opposite direction in the last 2 minutes. Sort of along the same lines, right? Say, given any open set, the pre-image is open. Right? We want to show that F is continuous at every X, right? Every X in R. Okay. Well, right? In other words, that given any epsilon neighborhood of f of x, there exists a delta neighborhood of x such that f maps the delta neighborhood into the epsilon neighborhood. Okay. Well, somebody gives you an epsilon neighborhood. Right? And we want to find a delta neighborhood that maps inside of it. Okay. We know that the pullback, if we pull this neighborhood back through, then the pre-image is open. Does anyone see it? I'll give you 10 seconds to say something. Any other?
So as the pre-image is open, do you know that there's a delta neighborhood?
That's the end. Exactly. Right. You say, well, look, F inverse. So given any epsilon neighborhood blah, we know that F inverse 1, 2, 3 is open. So, right, and contains X, right? So there exists a delta neighborhood of X in F inverse in the pre-image of the epsilon neighborhood
Given any epsilon neighborhood of what?
of F of X.
Oh, that's next.
Right. In other words, we're saying X is interior. Right? Right. Exactly. You say, well, look, if we take this is an open set here, we pull it backwards, and we get something open. We get something open because that's what our property, right? Pulling open sets back gives an open set. In that case, this is interior. What does it mean to be interior? It means that there is a delta neighborhood in here. Being in here means that this is in the pre-image of that. In other words, this neighborhood here gets mapped inside there. That's continuity. In other words, f of n delta x is contained in the epsilon neighborhood of f of x. So that's continuity. We found the delta neighborhood that gets mapped into the epsilon neighborhood. That's continuity. Okay. So different way of thinking about continuity. You notice that there's no deltas and epsilons evident here. They're sort of hidden. They're hidden in there in the definition of openness. But in fact, even if you don't have deltas and epsilons, one can talk about continuity. And so this is called topological continuity. Okay, that's it for today. That's it for today.